Today we are going to discuss the second topic of chapter number 3, which is the propagation of the transverse electromagnetic wave in lossy medium. So first of all, let us have discussion on the lossy medium. Lossy medium is a practical medium. The attenuation of the wave takes place in this particular medium, so the signal attenuates in this lossy medium. The loss will take place in this particular medium, so this is why we call it lossy dielectric medium. The conductivity, which is represented by sigma of this medium, is not equal to 0. So the conductivity, which is represented by sigma, is not equal to 0. So these are the characteristics of the lossy dielectric medium. Its conductivity is not equal to 0. It is a practical medium. The energy of the wave will decrease with respect to the distance traveled by the wave. This is why we say that the attenuation of the wave will take place in this particular medium. Well, as we discussed the transverse electromagnetic wave in the previous class, we discussed, you see, the properties of the transverse electromagnetic wave in this particular class as well. Well, we know that light is an electromagnetic wave. So basically, if you are talking about the propagation of the transverse electromagnetic wave in this particular medium, we are talking about the propagation of the light wave in a lossy dielectric medium. So in this particular topic, we will assume that the wave is a light wave and this wave travels in a lossy medium. The energy of the wave will reduce with respect to distance traveled by the wave. The attenuation of the wave will take place in this particular medium. Now, what are the characteristics of the transverse electromagnetic wave? We know that these three electrical quantities are perpendicular to one another: the electric field intensity of the wave, the magnetic field intensity of the wave, and the velocity of the wave are perpendicular to one another. So if the electric field intensity, magnetic field intensity, and velocity of the wave are perpendicular to one another, then this wave is known as transverse electromagnetic wave. This wave is also known as a uniform plane wave. So transverse electromagnetic wave is also known as uniform plane wave. You see, the electric field intensity of this wave is along x-axis, and the unit vector along x-axis is represented by ax. The magnetic field intensity of the transverse electromagnetic wave is along y-axis in this diagram, and the unit vector along y-axis is represented by ay. And the wave is propagating along z-axis, and the unit vector along z-axis is represented by az. So this is transverse electromagnetic wave. We assume that the light wave is transverse electromagnetic wave. The electric field intensity, magnetic field intensity, and velocity of the wave are mutually orthogonal. They are normal to one another. They are perpendicular to one another. And we assume that this light wave is moving along positive z-axis. Okay, so this topic is just like you see the previous topic. The only difference is that the conductivity in the previous topic was equal to 0. The conductivity in the previous topic was equal to 0, while the conductivity in this medium is not equal to 0. So this is the only difference between the mathematical equations of this particular topic and the mathematical equations of the previous topic. This topic is almost similar to the previous topic, so you guys will understand it very easily. So we are going to derive the equation for the electric field intensity of the uniform plane wave in a lossy medium. In order to derive the equation for the electric field intensity in the uniform plane wave, we consider equation number 8.1, and this is one of the 4 equations of Maxwell. So this is one of the 4 Maxwell's equation, that the curl of the electric field intensity is equal to minus j omega b. Omega is the angular frequency of the signal. This is the angular frequency of the wave. Now we know that beta is equal to mu h. We know this relationship. So what we do, we put the value of beta in equation number 8.1. We know that beta is equal to mu h. So if we put the value of the magnetic flux density in equation number 8.1, we get equation number 8.2, that is the curl of the electric field intensity will be equal to minus j omega mu h. So this is equation number 2. Now what we do, we take the curl of the quantity on the left hand side of this equation and the curl of the quantity on the right hand side of this equation. You know that we calculate the curl of a vector quantity, and the vector quantity on the right hand side of equation number 8.2 is the magnetic field intensity. So the remaining quantities on the left hand side are constant. So we will just calculate the curl of the magnetic field intensity because it is a vector quantity. So what we do, we take the curl of the quantity on the left hand side of this equation and the curl of the magnetic field intensity on the right hand side of equation number 8.2. So you guys can see this mathematical operation in equation number 8.3. We take the curl of the vector quantity of the left hand side of equation number 8.2, and we take the curl of the magnetic field intensity on the right hand side of equation number 8.2. This is how we obtain equation number 8.3. And we recall another equation of Maxwell. This is another equation of Maxwell which is in phasor form. So this equation says that the curl of the magnetic field intensity is equal to J plus J omega D, where J is the current density, the conduction current density, and D is the electric flux density. So we put the value of this curl of the magnetic field intensity in equation number 8.3. So let us put the value of del cross H, the curl of the magnetic field intensity, in this particular equation, right? So if we put the value of the curl of the magnetic field intensity on the right hand side of equation number 8.3, we obtain equation number 8.5. So we have put the value of del cross H on the right hand side of equation number 8.3. And we know that D, the electric flux density, is equal to the permittivity of this medium multiplied by the electric field intensity. So we know this relationship between the electric flux density and the electric field intensity, and we put this value of D over here in equation number 8.5. So if we put the value of D in equation number 8.5, we get equation number 8.6. So the curl of the electric field intensity is equal to minus j omega mu multiplied by j plus j omega epsilon multiplied by the phasor value of the electric field intensity. So this is equation number 6, which is obtained after putting the value of the electric flux density in equation number 8.5. And we know that the current density is equal to the conductivity of the medium multiplied by the electric field intensity. We discussed this relationship in the previous topic as well. So let us put the value of J in equation number 8.6. If we put the value of J in equation number 8.6, we obtained equation number 8.7. So we just put the value of J, which is the conductivity multiplied by the electric field intensity. That's the only difference between equation number 8.6 and equation number 8.7. We put the value of J in equation number 8.6 and we obtain equation number 8.7. So the curl of the electric field intensity will be equal to minus J omega omega mu multiplied by sigma, which is the conductivity of this medium, multiplied by the phasor value of the electric field intensity, plus j omega epsilon multiplied by the permittivity of the medium multiplied by the phasor value of the electric field intensity. Now what we do, we simplify the right hand side of equation number 8.7. So let us simplify the right hand side of equation number 7, and we replace j square by minus 1 in this simplification. So if you do it, we get equation number 8.8. Equation number 8.8 is the curl of the electric field intensity will be equal to minus j omega mu sigma e plus omega square mu epsilon e omega square mu epsilon e. So we consider equation number 8.8 and we rearrange this particular equation in the next slide. So let us consider the same equation in the next slide of this presentation. Well, we will do it in the upcoming slide. So we can show that the curl of the curl of the electric field intensity is equal to minus del square multiplied by the phasor value of the electric field intensity. We can show this particular relationship, and we know that del square E is basically equal to curly square by curly x square of the electric field intensity plus curly square by curly y square of the electric field intensity plus curly square by curly z square of the electric field intensity. We assume that in this particular equation, the electric field intensity is a function of x, y, and z. So this is the assumption in this particular equation. So what we do, we replace the left hand side of equation number 8.8 by minus del square E. Okay, so let us do it. So we replace the left hand side of this equation by minus del square E, and there is no difference you see on the right hand side. We have the same equation on the right hand side. We have minus j omega mu sigma multiplied by the phasor value of the electric field intensity plus omega square mu epsilon multiplied by the phasor value of the electric field intensity. Let's say this is equation number 6. Okay. So what we do, we rearrange equation number 8.6. So if we rearrange equation number 6, we get del square E plus omega square mu epsilon E minus J omega mu sigma E, which is equal to 0, and this is equation number 7. Okay. So this is equation number 7, and we rearrange equation number 7. So what we do, we take this quantity as a common quantity from these two terms. Okay. So if we take this common quantity from these two terms as a common quantity, we get equation number, well, I will call it equation number 8. So we get equation number 8. So you see, equation number 7 can be written as del square E plus omega square mu epsilon into 1 minus J sigma by omega epsilon multiplied by the phasor value of the electric field intensity, which is equal to 0. This is equation number 8. Okay. And in equation number 8, what we do, we replace this quantity by epsilon k, because this is a complex quantity, right? You see, this quantity is a complex quantity, and we replace this complex quantity by epsilon cape, right? This is cape. So let us consider this assumption. So what we do, we replace the quantity on the right hand side by epsilon cape, which is a complex quantity, right? So epsilon cape will be equal to epsilon into 1 minus J sigma divided by omega epsilon. You see, this is the permittivity. This is the permittivity of a lossy dielectric medium, and the permittivity of this lossy dielectric medium is a complex quantity because of this sigma. If sigma is 0, then this epsilon cape will be equal to epsilon. Okay. So if the conductivity is 0, then this permittivity will be a real quantity. It will not be a complex quantity. So I can say that the permittivity of a lossless dielectric medium is a real quantity, and the permittivity of a lossy dielectric medium is a complex quantity, right? So the permittivity of a lossless dielectric medium is a real quantity, and the permittivity of a lossy dielectric medium is a complex quantity, and this is because of the conductivity of the medium. If the conductivity is 0, then the medium will become lossless medium, and epsilon cape will be equal to epsilon. The permittivity will become a real quantity. Okay. So what we do now, okay, let us consider this equation. So what we do, we replace this quantity in this particular equation by epsilon cape. Okay, so let me clarify this cape. So if we replace the encircled quantity of this equation by epsilon cape, then we obtain this particular equation. We obtain this particular equation. So you see, we obtain this particular equation. Let's say this is equation number 9. Okay, so del square E plus omega square mu epsilon cape multiplied by the phasor value of E is equal to 0. If you come, this equation number 9 is known as the wave equation in a lossy dielectric medium. So if you consider this equation with the equation of with the wave equation in a lossless dielectric medium, the only difference you see between these two equations is that in the previous case this epsilon cape was equal to epsilon in this particular case. So if the wave propagates in a lossless dielectric medium, then epsilon cape in equation number 9 will be equal to epsilon. And as the wave is traveling in the lossy dielectric medium, that is why we have epsilon cape over here. So this equation is known as, I'm talking about this equation. This equation is known as a wave equation in a lossy dielectric medium. So this is the wave equation in a lossy dielectric medium. Now what we do, we know that the wave is traveling along z-axis. So the light wave is traveling in a lossy medium along z-axis. So z represents the distance traveled by the wave. Z represents the distance traveled by the wave, and this wave is traveling in a lossy medium, and we know that the signal will attenuate in this particular medium. The energy of the signal will decrease with respect to the power of the signal will decrease with respect to the distance traveled by the wave. And we know that the power of the electromagnetic wave is directly proportional to the amplitude of the square of the amplitude of the electric field intensity, right? So this is the relationship between the power of the electromagnetic wave and the amplitude of the electric field intensity. The power of the electromagnetic wave is directly proportional to the square of the amplitude of the electric field intensity. And as the power of the wave decreases with respect to distance, definitely the amplitude of the electric field intensity will decrease with respect to distance as well. Okay, so the electric field intensity of this light wave in this lossy medium will change with respect to distance. So the electric field intensity is a function of distance. The electric field intensity will change with respect to z only, with respect to distance only. It will not change with respect to x. It will not change with respect to y. It will change with respect to Z only. So the electric field intensity will change with respect to Z. It will not change with respect to X. It will not change with respect to Y. Right? So if the electric field intensity is a function of Z only, then we recall the equation for del square. Okay, where is the equation for del square? We go back and we recall this equation of del square E. As the electric field intensity is not changing with respect to X, so the second derivative of the electric field intensity with respect to X will be 0. And as the electric field intensity is not changing with respect to Y as well, so its second derivative with respect to Z will be 0 as well. And as the electric field intensity is changing with respect to Z only, so we will have curly square by curly Z square of the electric field intensity. So del square E in this equation will be equal to curly square by curly Z square of the electric field intensity. So let us replace this del square E in the wave equation by curly square by curly Z square of the electric field intensity. So we are going to replace this del square E by curly square by curly Z square of the electric field intensity. Okay, so we are going to replace del square E by curly square by curly Z square of the electric field intensity. So what we do, we replace del square E in the wave equation by curly square by curly Z square of the electric field intensity. So if we do it, we will get equation number 8.13. Equation number 8.13 says that curly square by curly Z square of the electric field intensity plus omega square mu epsilon k multiplied by the phasor value of the electric field intensity will be equal to 0. So we focus on equation number 8.13 now. This equation is known as second order homogeneous differential equation. So this is a second order homogeneous differential equation. We need to find out the solution of this second order homogeneous differential equation. So we are interested in the solution of this second order homogeneous differential equation. And in order to find out the solution of the second order homogeneous differential equation, we need to find out the characteristic or the auxiliary equation of this second order homogeneous differential equation. So we consider this second order homogeneous differential equation. We are going to find out its solution, and for its solution we shall have to find out its auxiliary or characteristic equation. So let us find out the auxiliary or the characteristic equation of this second order homogeneous differential equation. So in order to find out the auxiliary equation of the mentioned homogeneous differential equation, we replace curly by curly Z in the second order homogeneous differential equation by m. So we replace curly by curly z by m. Okay, so if we replace curly by curly z curly by curly z by m, so we get this particular equation. We have m square e plus omega square mu epsilon e which is equal to 0. Okay, so we rearrange this particular equation. If we rearrange this equation, you see the electric field intensity in this equation is a common quantity. So we treat it as a common quantity. We have m square plus omega square mu epsilon cape multiplied by the phasor value of E, which is equal to 0. And if you consider, let me call it equation number 14. So this equation number 14 says that the product of two terms is basically equal to 0. And if the product of two terms is 0, it means that one of the term will be equal to 0. So the electric field intensity is not equal to 0. Why? Because the electric field intensity represents the presence of the light wave in the lossy dielectric medium. If it is equal to 0, then it means that the wave does not propagate in this lossy medium. The wave does not exist in this particular lossy medium. So in equation number 14, we cannot replace the phasor value of the electric field intensity by 0. So if we cannot replace the phasor value of the electric field intensity by 0, we will replace the first term by 0. And this equation is known as the auxiliary equation of the second order homogeneous differential equation. And if you compare it with the auxiliary equation of the second order homogeneous differential equation of lossless medium, the only difference between this equation and that equation is that in that particular equation the permittivity was a real quantity, because the permittivity of a lossless medium is a real quantity, and the permittivity of a lossy dielectric medium is a complex quantity, and the permittivity of the lossy medium is represented by epsilon cape. So equation number 15 is known as the auxiliary equation of the second order homogeneous differential equation. We need to find out the roots of this particular equation. So let us find out the roots of equation number 15. So we find out the roots of equation number 15. If we find out the roots of equation number 15, there will be two roots. There will be two roots of equation number 15, and these roots will be complex. So let us consider the roots of equation number 15. Okay, so we find out the roots of the auxiliary equation, and you see we have got two complex root in equation number 8.17. This complex root is represented by gamma k, because it's a complex. So there are two roots of the auxiliary equation. The real component of this complex root is represented by alpha, and the imaginary component of this complex root is represented by k. So once again, we are replacing beta by k. K is known as propagation constant in the course of fiber optic communication system. So we replace beta by k. So there are two roots. These roots are complex quantities, and one root is positive, the other root is negative. What is alpha? Alpha is known as the attenuation constant of the electromagnetic wave. Okay. So alpha is known as the attenuation constant, and instead of beta we have k, and as I have told you guys that k is known as the propagation constant, right? So alpha is known as the attenuation constant and k is known as the propagation constant. We replace beta in all these equations by k, right? We don't use the symbol of beta over here because I have taken these materials from my book. I use the symbol of beta over here, and the book of fiber optic communication system use the symbol of k for this particular quantity. So the roots of the auxiliary equations are known. Once the roots of the auxiliary equations are known, we can find out the solution of the second order homogeneous differential equation. And where is the second order homogeneous differential equation? Let me show it to you guys once again. Here is the second order homogeneous differential equation. So we are going to write down the solution of this second order homogeneous differential equation. We are going to discuss the solution of the second order homogeneous differential equation now, because the roots of the auxiliary equation are known. So if the roots of the auxiliary equation are known, you guys can find out the solution of the second order homogeneous differential equation. The solution of the second order homogeneous differential equation will be in the form of equation number 8.18. So the phasor value of the electric field intensity will be equal to E naught into e raised to power minus gamma z. You see, this is one root which is negative and which is complex as well, plus EB into e raised to power gamma z, and this is another root. So these are the two roots of the auxiliary equation. So if the roots are known excuse me. So if the roots are known, we can find out the solution of the second order homogeneous differential equation, and the solution is given in equation number 8.8. And what is AX? AX is a unit vector along x-axis. So if you guys recall the diagram, the electric field intensity was along x-axis. So electric field intensity is a vector quantity, and the direction of this vector quantity in our diagram is given by this unit vector AX. So this AX basically shows you the direction of this vector quantity. So anyhow, this will be the solution of the second order homogeneous differential equation. So what we do, there are two components. Once again, there are two components of this wave. This component travels along positive z axis, and this component is known as forward traveling wave. Okay, so the first component of the electric field intensity travels along positive z axis, and this component is known as forward traveling wave. The second component travels along negative z-axis in the backward direction. So uh, this component is known as backward. Let me represent it by B, backward traveling wave. So this is forward traveling wave, and this one is backward traveling wave. So there are two components of the wave. The first component travels along positive z-axis, and the second component travels along negative z-axis. But if we look at our diagram, let us consider the diagram once again. I go towards the diagram of this particular topic. Here is the diagram, right? So we consider this diagram. If we look at the diagram, the wave travels along positive z-axis. We have assumed in this diagram that the light wave is traveling along positive z-axis. No component of the wave travels along negative z-axis, right? So if no component travels along negative z-axis, then we don't need to consider this component of the wave, the component which travels in the backward direction. Well, this component exists in a different scenario. I will discuss it later on. You see, if the reflection of the wave take place, then there will be there will be two components in that particular medium. One will be the incident wave, the other one will be the reflected wave. The incident wave will be traveling along positive z-axis, the reflected wave will be traveling along negative z-axis. So in that particular case, this component will exist. But over here, our wave is moving along along positive z-axis. No component of the wave moves along negative z-axis. So this is why we are going to ignore this component of the wave in the solution of the second order homogeneous differential equation. So let us consider the solution once again, and let us ignore the second component of this wave. So you see, we consider this component because this is the component which travels along positive z-axis, and definitely our wave is moving along positive z-axis, and we ignore the second component of this particular equation. Why? Because this component represents the component of the wave which moves in the backward direction. So this component does not exist. This is why we eliminate this component over here. We delete this component over here. We don't consider this component over here. So we consider the first component of the phasor value of the electric field intensity. So let us consider the first component in equation number 8.19. So we just consider the phasor value of the electric field intensity in equation number 8.19. So the phasor value of the electric field intensity will be equal to E naught into e raised to power minus gamma cap z. So what we do now, we put the value of gamma cap in this particular, we are going to put the value of gamma cap in equation number 19. And what is gamma cap? If you recall gamma cap is basically equal to, this minus gamma cap is basically equal to minus alpha, this is minus alpha minus j k. Okay, I am not going to consider beta, I will consider k in this particular equation. तो इन equations में जहाँ जहाँ पे आप लोगों को बीटा नज़र आएगा उनको आप लोग k से replace करें. So we put the value of gamma in this particular equation, that is equation number 19. If we put the value of gamma in equation number 19, we obtain equation number 20. There is the phasor value of the electric field intensity will be equal to E naught into e raised to power minus alpha z minus j kz. So please replace this beta by k minus j kz. Okay, so this is the phasor value of the electric field intensity, and we are going to write down the instantaneous value of the electric field intensity. So here is the instantaneous value of the electric field intensity. So the instantaneous value of the electric field intensity is equal to E naught into e raised to power minus alpha z into sine of omega t minus kz. Replace this beta by k. Okay, so we have minus kz multiplied by ax. So this is the instantaneous equation of the uniform plane wave, the light wave in a lossy dielectric medium. Okay, so what we do, we focus on the instantaneous value of the electric field intensity in this particular equation, and you see the amplitude of the electric field intensity is E naught into e raised to power minus alpha z. You see, this is the amplitude of the electric field intensity of the uniform plane wave in a lossy medium. And you see the amplitude of the electric field intensity decreases exponentially with respect to time. If we plot the amplitude of the electric field intensity with respect to the distance traveled by the wave, so let's say this represents the distance and this coordinate represents the amplitude of the electric field intensity. So the amplitude of the electric field intensity decreases exponentially with respect to distance. So this is the amplitude of the electric field intensity of the transverse electromagnetic wave in a lossy medium, and it decreases with respect to distance. We discuss the power of this wave. We know that the power of this wave is directly proportional to the square of the amplitude, the square of the amplitude of the electric field intensity. So here is the amplitude. We have E naught into e raised to power minus alpha z, and we have square over here. So the power of, let me make this equation a bit clear. Okay, so this is 0, okay, E naught. So the power of the wave is directly proportional to the square of the amplitude of the electric field intensity, and here is the amplitude. So this power will be equal to a constant, okay. So it will be equal to a constant multiplied by E naught square into e raised to power minus 2 alpha z. Okay, so the power of the electromagnetic wave will be equal to a constant multiplied by E naught square into e raised to power minus 2 alpha z. And if we focus on this particular equation, you see the power of the wave is decreasing with respect to the distance traveled by the wave, and this phenomena is known as attenuation. So the energy of the wave will decrease with respect to the distance traveled by the wave in this particular medium, and this phenomena will be known as attenuation. So if we plot the power of the wave with respect to its distance, so z represents the distance traveled by the wave and p represents the power of the wave. So if we plot the power of the electromagnetic wave with respect to the distance traveled by the wave, so the power of the wave decreases exponentially with respect to the distance traveled by the wave. This phenomena is known as attenuation. So this graphical relationship gives you the attenuation. It gives you the attenuation of the wave. Okay, so the signal will attenuate with respect to the distance traveled by the wave. So lossless medium is an ideal medium, and the attenuation of the wave does not take place in this particular medium, while a lossy medium is a practical medium. The attenuation of the signal take place in this particular medium. This is big enough for today. I will see you in the next class. Thank you so much.